measurement matters, because really if you write this out, it says AB times BA. Or in other words, if you would first measure A and then measure B, or you would have done it the other way around, if it didn't matter, then the outcome would have been the same, this would be 0. And now we have seen in quantum mechanics that if you have measured one thing, then the other one has become uncertain. So in other words, it is impossible to measure one thing and then the other, or the other way around. It will give you, in general, different answers. How much difference? That is given by this C over here. So if C is a big number, then it means that these two things highly don't commute. In other words, that measuring one thing will really mess up the measurement of the other. That's what a commutator tells you. I'm going to make one other statement, and I want to see if you understand what I mean. It's also a measure of whether two operators have the same eigenstates. Does that make sense? That is important. Sure? Everybody? Yes. But let me say the sentence first, and then you can parse word by word. If this is 0, this commutator, it not only tells you that the two operators commute, that it doesn't matter which order you do the measurements, it also tells you that the eigenstates of one operator are also the eigenstates of the other operator.
If they commute?
If they commute. If the outcome of this thing is 0, then you know that the eigenstates of one are also the eigenstates of the other. Those are two equivalent statements. There are not two different statements. One of them is mathematically equivalent to the other one. In a certain way, it's the more important version of this statement because it tells you something about measurement. Suppose I have two operators and they commute. It just so happens that this is equal to 0 for those two operators. At the moment that I've measured one of the operators, I get a number out. From that moment on, my general state will be in the eigenstates of that operator. That's what we saw one board before. Now I'm going to do the other measurement. Now we just saw that these things have the same eigenstates. So that means I've put it into the eigenstates of operator A, but it's also an eigenstate of operator B. So is there any uncertainty what will come out for B then at that moment? The answer is no. Because one definition of an eigenstate is that you know with 100% certainty what the outcome will be. So really, this is just another way of saying whether you are 100% certain that if you measure A, that a certain number for B will come out as well. I really have to be sure that everybody has understood this.
Does it mean that they share, or that all of them are the same?
They're the same. They have the same number, and each and every one is the same.
Okay, so they have all of the eigenstates are the same.
Yes.
And if they don't commute, then does that mean that they don't have the same eigenstates?
Yes.
Yes.
They might have a number of same eigenstates, but generally the whole set is different. There are differences. By the way, also a very important statement. They have the same eigenstates if they commute, but they don't have the same coefficients. Okay, it's not the same decomposition. It's not the same linear combination. The eigenstates are the same, the numbers in front of the eigenstates are not the same. The eigenvalues are also not the same, of course. Like I said a couple of days ago, I wasn't here when you did your quantum mechanics course, so we really have to do this in a discussion type of way, so both parties know exactly where we are. So this is why I'm asking every now and then, does everybody understand, has everybody seen this before? Because I have to take it next week as a starting point. Okay, back to the physics. We're going to do mathematics in a second, but back to the physics. As I told you, the importance of this thing is that it tells you that you cannot know values of two things at the same time. Okay? Now, if they share eigenstates, you can know that. You can know with 100% certainty of both. Okay, let's go through this. It's a good thing. I mean, it just means that if you know what the commutator relation is between two operators, as we did in exercise 2, then you know from that moment on exactly how certain you can measure one compared to the other one. Alright, let's go through the mathematics. This might take a while though, but it is important. Everybody good? Ready to rumble? Okay. Goes the steps. I'm showing you now the version that it did, not the one that I did on the train, which was nice too, but a different version. This one is a little bit faster. We use a special trick that I didn't think of. Okay, there we go. It starts by looking at the uncertainties. We're going to rewrite them in a more manageable form. Delta A, well, here's the definition. And it is easy to show that this is just equal to this. This is wrong, excuse me. It's the same thing. It's not extremely trivial, you have to write down a couple of lines before you get there, but it is the same thing. Now why we're going to write it in this way and not retain this way, it's simply because the mathematics becomes a little bit simpler later on. This is a step that I didn't do. My derivation was fully this, and then I took a page or two longer or so. This is a lot faster. Now what I want to do is show that this really is equal to that. I think that's going to be worthwhile. Just to see how that works. So we're going to put this step right. So start out with the full definition. No, you know what? We're just going to take this one, work it out, and see what comes out. Now, as you know, this is an expectation value. So it's really just shorthand of having bracketed this operator. You see that it's an operator, yes? A is an operator, so any strange combination of things is also going to be an operator. And this thing means an average. I'm going to average out, and averaging, as we saw before, is just squeezing in between brackets. So with this thing, I'm going to write down this. This is no physics, it's not even mathematics, it's just semantics. This is just another way of writing what we started out with. Now, in between here, we're just going to treat them as if they were numbers. They're not numbers, by the way, these are operators, yes? I'm already omitting the hats. I should be more careful. These are hats. Okay. This is why I don't like writing hats. It takes forever. There you go. And this one. But we're going to treat them as numbers. Is there anyone who knows the justification for that? Why I can treat them as numbers? We only need one word. Right? I mean, I'm just going to write down this square as if they were numbers, so that's a squared times 2a. And again, I'm pretending as if these are numbers, so I can use your usual squaring out. Why is it allowed?
Because they're Hermitian operators.
They're Hermitian. Or that's even too strong a statement. I mean, it's correct. The fact that they're linear is enough.
Okay.
They're linear operators. And almost all operators in quantum mechanics are linear and or Hermitian. So yeah, the fact that this is allowed is really because they are linear operators. I think I told you last time about this mathematics professor that I had at VU University. He always said, well, you know, if you as a physicist are not sure whether something is mathematically correct, just pretend that it is. First see if it gives you something that you want, and only then go and check if it's correct. This is correct. We're allowed to do this. And averaging is itself a linear operation, so you can really just do the averaging of this one, and that one. This is not quantum mechanics, by the way, or the property of the operators. This is really just a property of the procedure of averaging. A plus B average is just the average of A plus the average of B. That's what I'm using here. Here's an interesting one. Can somebody tell what comes out of this, the averaging of that one? Funds. Well, let me just write it down like this first. Psi, a hat, average. Look at this beautiful thing here. And then there's this one coming in a second. Looks complicated, yes? You have an average, squeeze in between an average.
You just move it out so it's like psi squared on both sides, or not?
I don't think I follow. What do you mean?
It's
No,
probably-
you might be right. It's just I didn't pick it up.
No, it's okay.
Let me ask a intermediate question. What kind of object is this? The A. Should be more specific in my questioning. Is an operator? Is the number? Is the function? What is it? What is it? A itself.
Well, we're treating it as like a number, right?
Yes, you're right. When I did this step, I'm now back to treating it as operators. Here's the answer. It's an operator. But what is this thing?
What's the number?
That's a number because it's already an average.
Well,
And
then
numbers.
just into
Yeah, exactly. You can put it in front because numbers. You can just put it in any averaging. If you multiply everything by 4, it's just the average of everything having been multiplied by 4. So what I'm going to do now, I recognize that this is a number. I'm going to put it in front of the rest. So let me write it down below here. So what we have here is A, which is a number, times everything that I'm still left with. This is still the same thingy. And does everybody see that this is really just the same thing? Because this is shorthand notation for an average, right? And here's the average. So really what we have here is minus 2 times the average. There you go. I'm going to erase this and going to write down the final expression here. So minus 2 times average of A. There you go. So that's that part. And then there's a final part. What kind of object is this?
Average squared.
Yes, but it's an operator, it's a function. Write it out first, that's what it is. This thing right here. Number, operator, function, limitic.
Number?
That's a number. I mean, this thing by itself is already a number, so squared is also going to be a number, and numbers you have to put in front of everything. So this will just give you a number times this. Okay, back to our postulates a couple of days ago. What is this?
1.
That's 1. Because you can normalize state functions. So there you go. I'm going to put that there to have everything in place. And I'm going to write it down as help me out here. This is correct? No? Is this wrong? I wrote it down just a second before.
Well, it's true.
No, it's just the same thing. Okay, yeah.
Squared.
There you go. I'm being a little bit inconsistent with my notation because here I put the sides where explicitly I wasn't going to do it here. It's the same thing.
Aren't you missing a square in the middle?
Yeah.
I think I am. Yes. There you go. Thank you. As you know, I do these things in real time, so I really need your help to get me through this. But it's just out of interest. I know that there's a number of teachers here and everywhere that like to use PowerPoints to go through calculations. And I myself am not a fan of these things. Because when my professor did it back in the day, it was really like, well, we have this equation, and then if you do this click, then this comes out, and click, and that comes out. And the nice thing about doing it together is that you actually see it happening. You can see where all the steps come from. But it takes a little bit longer though, but I do think it's worthwhile. Okay. And then there's another square here, yes?
Yeah.
Now look at this beautiful thing that we have here. Minus 2 times this thing, plus 1 times that thing. I think we can easily conclude. Because it's, despite its complicated appearance, this is just a number, that is a number, it's the same number. Minus 2 times the number plus 1 time that number gives you minus that number. Everybody in agreement? Alright. Now it already starts looking like this, because we were on our way to prove that our, where is it? we're on a way to prove that this is equal to that. And I think we're almost on our way now. So this thing we have now seen really is equal to this. Minus so this is something that we have proven so far. You know what? I think I'm going to switch gears for a moment. If it's okay with you, I think I would rather first go through all the way of getting this to be equal to that, because that is the meat. This part being equal to that part, we're halfway there, but let's park that for a moment and get back to that. I would really like to go through the bigger calculation. You look troubled.
Aren't we already there?
Are we?
This is square root.
Oh yeah, the square root, okay.
Yeah.
Sorry.
Exactly, yeah. It's an easy calculation, but it's more algebra than there's any physics involved, so preferably I would take this as a given now. We're almost there, but if we have some time left at the end, we can finish the rest of the lines. But this is more algebra than it's physics, so I would like to continue here. Because what we now need to do is, we are now able to write this thing as this, multiply them with each other, and see that that comes out. Now here's the trick that I didn't use, but is ridiculously smart. You see, what people did is they showed that this thing you can write by itself as a state. You see, in the derivation you can do is you can define a new thing. This is really how mathematicians work. They just define something new, and within the new definitions things become easier. This is why it took me an hour extra to get to the end result, and they did it a lot faster. We're going to define a new state. So we're going to take our original state that we're taking the average of, and we're going to redefine it as this thing. There you go.
So is that L or F?
That's an F. Yes. It's really just a name. There's no physics involved or anything. I prefer not to call it L because of my confusion with angular momentum or so. It's just a state. But the only thing that's important right now is that you see that you're just allowed to do this, right? I mean, you have this state, you use a couple of operators, you get some other thing. Now, why is that a handy thing to do? Let me just write it out for a second. It's really a combination of this thing minus that thing. Why is that a good thing to do? Because you can now show that this one, delta E delta A squared, is equal to this. This you can now show. Again, this takes a couple of lines of algebra, it's not difficult. So what we've done now is, we've seen this, we've redefined it using this F, and then you can show that this delta A with the square is just this bracket. There's a reason for doing this. The reason is that if you do this, you put all your operators on the rug. We're going to do the same thing with G, with operator B in a second. We're going to define a new get, where we're going to put all the B's in, put everything on the rug, under the hood. And as a result, the end expressions that we're going to work with from that moment on are completely free of A's and B's, and we can just use the basic postulates about cats. It makes the calculation a lot simpler. Again, this is something I did not do myself. So we're going to do the same thing for B. So B, because we also have this thing right here, which is going to define as such. There we go. There it is. And as a result, the uncertainty squared is G. Again, the upshot of this is, the cleverness of this is that from this moment on, now we have the delta A's and B's having written now as states, as cats. That means that we can evaluate this without having to look at the details of the A's and the B's. It becomes much simpler. Before we continue, here's the outline. We're going to square this expression here. So we get a delta A squared and delta B squared, and then we're going to replace them by these two, right here. Has to be bigger than something. If it's bigger than something, in a moment, I'm going to use something that is called the Schwarz inequality, which is a standard notion from linear algebra. And this is, again, one of my questions to you. Have you seen that before?
Yes.
Yes? You have not?
No.
You have to go.
I have seen it before.
You have seen it. You know what it is?
I don't know exactly what it was here, but I always think of it as the thing with, like in a triangle, that
Yes.
two arms are always longer than one arm.
That is true. That is true. It's a more general statement though. Just as a step back, give me the outline, I'm going to fill the details later. If you have two vectors just in normal space, then you know that if you have two vectors and you make a triangle out of that, then one of them is going to be bigger than both of the other ones. Right? It's Pythagoras theorem, I guess, or cosine rule. This also holds in any vector space. It doesn't necessarily have to be a space of positions, the normal vector space from linear algebra. It works for every single piece of mathematics where you can write down a general point as a linear combination of other points. So it also works in cat space, in our Hilbert space, this space of cats. It's called the Schwarz inequality. We're going to use it in a moment, so let me just write it down for a second. In our particular case, it says this, that if you have the product of these two things, it's always going to be bigger than this particular bracket. Schwarz inequality. Again, it holds in all vector spaces. Doesn't necessarily have to be our vector space of quantum mechanics, it holds in all, under a certain number of conditions as a linear vector space as such. You can already see where this is going to be put in, yes? Because look at what we have here. We have here A times uncertainty A times uncertainty B. I'm going to square it in a moment. But we already know that the square is equal to these brackets. So if we square this, then the left-hand side becomes exactly the form of the Schwarz inequality. And then we know it's going to be bigger than this. So in a moment, what we're going to do is then take this and prove that it really is equal to that. And then we're done. Then we have it. I want you to take real careful note that despite all the mathematics that might be new to you here and there, maybe this inequality of just we're using with this Hilbert space, the only thing we're putting in is mathematics. I'm not smuggling in any physics. And the fact that you can write things as brackets in quantum mechanics, the fact that you can write a information state in this vector space is enough to get the Heisenberg uncertainty relation. Whereas in some other quantum mechanics courses, what you usually get is it's an experimental fact that you plug in from the outside. It isn't. It's already built in from the outset. Okay, so everybody okay with the outline? Before we continue, is there anyone who would like to see that this is true? Because it just made it as a statement, it's algebra. My preference is, let's go through the steps, and where needed later on we can fill in the algebra steps, okay? So given that it is a fact, again it is just mathematics, no physics involved. There you go. Then let's take this bad boy here and take its squared. I'm going to take modulo squared. Why? Well, just because I can. It's okay as long as you do it on both sides. There we are. Same expression. Delta A, because of our clever mathematical trick, we can now write as a bracket without having to look at A's and B's anymore. This thing is exactly that. That thing is exactly that. And here's the Schwarz inequality that I'm putting in now. Schwarz size is bigger than this. There we go. Okay, now we need to look at this one. This one. Now we have to go back to A's and B's just for a second just to work out what that is. Because we know what F is, we know what G is. We just write it down again. G is, here it is, by definition, the average of B. Both of them working on this state psi. And F is A minus average of A working on this state psi. Now I don't need F, here's a cat F, I need a bra F. How do I make that one? It's a complex conjugate. And if you want to be really pedantic about it, it's the Hermitian conjugate, but Hermitian conjugates only differ from complex conjugates in monotonic vectors. There you go. It should be this. I'm free to drop this one, by the way. That one right there.
I was going to say because it's a number, right? So
Well, it is a number, but numbers differ from their complex conjugates. In this case, it doesn't. Again, this is me asking about your previous quantum mechanics experience. Why can I drop this star over here?
Because they're one and the same.
Yeah.
Well, yes, that is true. That the average complex conjugate is the same thing as the average.
Yeah.
Well, from a physical point of view, that makes sense because the average of a measured quantity, well, measured quantities are always real. They're never complex numbers. But that's sort of cheating. I mean, why is it, from a mathematical point of view, why it is real? And the answer is Hermitian operators. You can prove that Hermitian operators always have real eigenvalues, no complex eigenvalues. So if you take any Hermitian operator that operates on its eigenstate, you get back an eigenvalue times the eigenstate, and this number is always real. And this number you get out of your measurement. So if you have real numbers, you take an average of a real number, what comes out is a real number. So this is a real number. And a real number means we don't care about complex conjugates. There you go. Go to erase this. And then move on. Okay. What's your preference, by the way, break-wise? Self-sum?
That quote's not.
No, it's about 10-2 or so.
It's, yeah, 5-2-ish.
Okay. Okay, let me just first write down this and take a break for a second.
Okay.
So this thing, Fg equals, I'm going to put in the F, the bra. There you go. Average, another bra. And put in the G's. There we are. And And just play around here for a little bit. Because there are now two sets here. Just going to take this one, do it with that one, just work out the brackets. Oh, hi. No, that's fine. Welcome back. This is of course just us doing the algebra. There you go. There it is. Okay, help me out here because you can simplify. There's stuff in here that can be simplified using some tricks that we did before today. We're doing exercise 3 by the way. The Heisenberg uncertainty.
The last two terms follow away against each other.
Let's see. Yeah, you're right. Look at that.
Because
Isn't that beautiful? Yeah, you're right.
yeah,
Absolutely.
B is an average and the psi
you're right.
is
You see,
1.
A is just B, right?
Yeah.
And this is just equal to
1.
unity. So there you go. So A times B minus A times B, the averages, they cancel each other out. And this other one, also can be simplified somewhat. Because what kind of object is this? That's a number, it's an average. And numbers can be put in front of the bracket. So just take that one out. And what we have here is psi A star psi. And then, unless I'm extremely mistaken, this itself is just the average again.
Yeah.
So minus. There we go.
It's the average of the conjugate, right?
Yes, thank you. Yes. But here's the thing. The average of the conjugate, you can take the conjugate out of the averaging, but we already know it's going to be a real thing anyway.
So it's the same.
Might as well
Yeah.
leave it out. The same thing here.
Oh, great.
So life becomes easy. I think this is extremely worthwhile exercise. I mean, it's practicing in both the bracket operation and just physically knowing what's going on at every single step. So ultimately,
Why is the conjugate gone for A in the last step?
because a complex conjugate you can take out of a bracket. If you do the algebra, you see that it doesn't matter if you first take an average and take the complex conjugate, or you take the complex conjugates and take an average out of that. You can just take it out. And because you know that one of them is going to be a real number, right? The average is a real number. So the complex conjugate of the real number is also going to be a real. You can drop the complex conjugate. That's what I did here. Okay, we're really close now, because, and this I think is going to be a good time to take a break. But we've seen now that, just go through the derivation just for a second, but we started out with this thing that we had to prove. We first showed that you could rewrite the uncertainty in a different way by making these two new definitions. It turned out that this inequality can be written as this inequality. So delta A squared, delta B squared are just these two thingies squared. And the Schwarz inequality tells you it should be bigger than this bracket here. And again, Schwarz inequality holds for all vector spaces, so also for Hilbert space, R space. The next step that we did was, okay, well in that case, let's calculate this bracket, and we find that it is this expression. So the only thing we need to do after the break is show that this is indeed smaller, or excuse me, bigger than that. And then in some way put the C in. And then we've shown everything that everything's true. By the way, does anyone see how we're going to put the C in a moment? Little clever mathematical tricklet. And we have this expression here. This part we already have, but there's no C in there yet, yes? We need to get the C in somewhere.
Maybe you just define it as that.
Oh, no, we're not, no.
Math sheet.
Yeah, that's what we usually do in mathematical physics. When we have an answer we don't like, we just redefine everything and get rid of numbers and everything. Not in this case. No, C has already been defined, right there. We're not free to define it in our own little way. But here it is. Because look at this. A times B. Well, A times B minus B times A is this commutator, yes? So playing around with a little trick, we can get the C in. I'm going to explicitly use the definition of this commutator to replace this one with something with a C, and then everything will work out beautifully in a second. You look happy.
I'm a little scared, but alright.
What is the frightening part?
Oh no, it's just a lot of maths.
I agree. I agree. It's an abstract way of doing things. Unfortunately, there's almost no way of getting around it. The other way will be to postulate things. Well, this is true, that is true. And despite it being a lot of mathematics, the nice thing about it is that the only thing that we've done 3 days ago was start with 4 postulates. And everything that has followed since then is the direct mathematical results of those postulates. And that to me is a much more elegant way of doing physics. It's more abstract, I agree with that. But starting out with the fewest number of starting points, instead of having to add on things along the way, the more robust your theory is going to be. So yes, lots of mathematics, but it is worthwhile. Okay, I think this is about break time then. Okay, I'll see energy levels. Your energy levels. No, yours. If I do my Hamiltonian on you, what is there a high probability that we can continue? Is
Yeah.
the people ready? Yeah? Okay. Good. We're almost there.
Sure. Why is in the raw version of F? Where does the second wave function raw come from?
I'm not sure what you mean.
Yeah,
Here's the graph of F, yes.
Yeah. Why is there two?
Oh, this is multiplying out this one. If you write this like this, so it's 2 of them now. Then you take the complex conjugate, which just means everything gets complex conjugate, and this one becomes a graph, this one becomes a graph, and you get exactly that expression.
Yeah, because it's no longer there's no longer the brackets, right?
No. It's not a bracket. F is not a bracket. It's a state. Okay, so close. We're so close now. All right. We ultimately found out what F and G was. We found that it is this expression right there. And here's the next step. There we go. This little tricklet. There's a little side note. It's a clever mathematical trick. That if you have this thing right here, F, G, this thing, suppose I want to square it. Not just a square, I take a modulo square. Modulo square. There you go. Okay. So everyone agree that this is equal to that? It's not just taking the bracket and squaring it, it's taking the bracket with the G and F reversed.
Why do you reverse it?
Because this thing means that I have to multiply this thing by its own complex conjugate.
Oh.
The complex conjugate of a bracket is the same thing with everything replaced. You can immediately see it by the definition of a bracket. Yeah. Okay, now here's something interesting, because we know that this is a number, some complex number. This is not a real number, by the way. An average is a real number. And an average means something that you take a bracket with an operator in between and make this bracket out of this. This is not this kind of thing. Because what we have here is this thing with a bigger thing in between. There's no certainty that this is going to be a real number. But it doesn't matter for my argument because this is going to be some complex number. It's called z. And here's the same number, complex conjugate. And you know what comes out of a number times its own complex conjugate, yes?
Real number.
Sorry?
Real number.
It is a real number. It's actually the length of the vector in the complex plane. You can always write the complex number as a times, or a plus b times I. And here's a minus complex conjugate. You work out the brackets, you get a squared plus b squared. And by Pythagorean theorem, that's the length of the vector. And you're right, that this is a real number because a is a real number and b is a real number. The only complex part in this z is in the I here. That's not in the final expression anymore. So we know something. This is real and it's bigger than it's also bigger than 0. Bigger or equal to than 0. That means it's also bigger than b. Do you agree with that? I mean, the smallest value that a squared can have is 0. So the smallest that this can be is b squared. And everything else, the a squared can only make it bigger. So it's bigger than this number. Alright? Now b squared, for any complex number, I can write in the following way. Modulo squared. Now why on earth would you do this? It's true though. Let's prove this part, just for a second. Because we're going to continue with this, and we have to see that's really the same thing. Now this, just a second ago I called z. So it says z here. Minus. Yes? Now z, we can always write as a times like this. So far so good? I'm really just proving this part here, that this is true. Do you see that the a's cancel? What do we end up with? B times I, 2 times minus minus gives you B. In other words, this thing is bigger than b squared, which is now proven, and b squared itself you can write as this. There's a reason I was asking you for your energy levels, because yes, it's a lot of math and I have to plug everything together because we have pieces now. One piece is this. This is bigger than that. It's piece number 1. Piece number 2. This thing can be written as this. Piece number 3. This thing is by itself bigger than that thing. And now put everything together. So I'm going to erase everything except for those key ingredients and then put everything together and then finally end up with this thing right here. If you can already almost see how we're going to get there, because look at this. These two together, plug in, and we're going to do it in detail in a moment, but maybe you can already see where I'm going. FG, GF. Look at this, FG, it's an average of an A and a B, minus GF, which is going to be the same thing with a B and an A. So you get AB minus BA. Sounds familiar? It's going to be a commutator in a sec. That's where we're going to get the C from. So why are we doing this trick, little trick over here? Why would you write B in such a complicated way? Explicitly, so we can get the commutator in. Okay, going to erase everything except for the key ingredients, which is this. This thing ultimately is bigger than that thing. That is the conclusion here. So let me write that down. It's bigger than the rest I will erase. There you go, that's one ingredient. Another ingredient was this thing right here. Yeah, that one. Erase this. And the final ingredient was that Fg is equal to minus B A. Okay. Anyone wants to take a shot at this? We're so close. We're so close. So close. Everything is up there. This is Schwarz inequality. This thing is by itself bigger than this expression. Alright, we plugged ingredient 1 into ingredient 2. I need help here. So close. This one we've used, that one we've used. We haven't used this one yet.
You can fill that one in there.
Exactly. Exactly. Because we have Fg here, and we took a painstaking course in calculating what that is in terms of A and B.
Then the average B and the average A are going to cancel out.
Yes. Why?
So
Why? You're right.
Because if you put it in there, you're getting a minus A and B from the first term, and you're going to get plus A and B from the second term.
That is right. Absolutely.
And then you're going to get 2 times IC.
Yes. You're already there, right?
There.
Oh, look. I see the old big smile of understanding.
I found this in the Griffiths book, except that last part was not explained.
Oh, yeah, the introduction to quantum mechanics by DJ Griffiths.
Yeah.
This is in there, yeah?
Yeah, but I didn't get the last part, so
Well,
now I finally know how to do it.
Okay, well, that means that we've done something good today. Look at that. You've made my day. But you're right, this part, we already know how to write in terms of A and B. So it gives you 1, 2A, and just going to abbreviate it for a second, right? You know that this is just shorter written like this. There you go. B, A. Did you solve it using Griffiths?
Well, I mean, I had most of what we did before written down, but I didn't get the last few steps.
Okay.
So that's why I'm like, I don't know.
Okay. No, modulo squared. I just put the ingredient in, 3 in. And you're right, look at these. Cancel each other out. Look at what we end up with. There's almost no bigger satisfaction than seeing a calculation work out beautifully in the end. I am not joking. Remember the first time in my PhD time that I had this idea of, wait a minute, I think this should work like that and that, and people said, no, it can't work like that, and I worked it out and it worked ultimately. I felt like being alone for like 3 weeks. just because nature and I had understood each other a little bit. Really, that is a great feeling. Okay, but we're there now, right? Because this thing here is really just 2i, and then the average of AB minus BA. There's that. And this thing, I think, is exactly what is the commutator. So the average is the commutator. And the commutator we have an expression for. Because here is, according to our starting point, is A times C. So what we have here is the average of this operator C with an I in front, 1 over 2I here, and you know with numbers, even imaginary numbers, you can just take in and out of averaging. So this I cancels, oh, that I over there. Oh. Leaves you 2 over there. And you end up with equals 1, 4, and there you go. Everybody agrees?
Wait, can you explain the C thing again? I missed that.
What's that? From here to there?
Yeah.
Okay, that is just the definition of our commutator.
Oh, yeah.
We said that at the beginning this whole thing will hold at the moment that our commutator A and B has this property. And there we go. Now, in order to do all of this, I took a square everywhere, the modulo square. Now take the square root of that, and you end up with exactly our Heisenberg uncertainty. This one right there, the one that we have to start with, the one that we set out to prove.
So which part over there is the commutator
This
definition?
from there to there. Now, despite having used a mathematical trick here and there is no smuggling involved. I really want to emphasize this point. Yeah, because you can smuggle, right? You can say, well, this part I don't like, it is going to redefine stuff and everything. There's no such thing going on right now. We just had these definitions, we did a whole lot of rewriting. We used 2 inequalities. The Schwarz inequality, that holds in every vector space. And we used a second inequality, namely this one, that this thing is always bigger than that thing. And then the rest was just painstakingly working out the mathematical details. Final conclusion, delta A, delta B is indeed bigger than the average of I times C.
I found what I did wrong. The 1 over 2i and then times fg.
Yes.
I had the second one as fg again instead of gf.
Oh yeah,
That's
okay.
why I did it like that.
Okay, well it's crucial, we did it over there just a second ago, that you understand that fg is the complex conjugate of gf.
Yeah, that's because I got minus 2 times the average, and
Okay.
the I and the C cancel each other out instead of the other way around.
Yeah, exactly. If you forget about this complex conjugate part, and you think that fg is really just gf, you end up with a minus sign difference somewhere in all the terms that have an I, and that cancels out the C.
Yes.
Okay, so there we go.
Why do we have 1/4 times C?
Oh, well, it's because of this square.
But instead of we mean I, right?
Let's see. You're saying that there might be a mistake somewhere?
Oh, no, we have. You're saying that we need I.
Oh,
We
never
have.
mind, never mind. I
Yeah?
was looking at it.
Because I wasn't sure what you were asking, but.
Oh, I was looking at the wrong thing.
Oh, okay. So okay. No mistakes on the board. It's just okay. Good. All right. Now, forget about the mathematics for now. The key point, of course, is this. We're now going to apply it for a situation. From this moment on, you can just assume that this holds, right? We've gone through the derivation. It takes us about an hour and a half or so, but you ultimately get there. Again, the only thing I've used are the postulates of 3 or 4 days ago. It's already built in there from the outset. Just as a couple of comments. When you use older texts on quantum mechanics, what they typically say is, well, the reason that you have Heisenberg uncertainty is that because if you do one measurement, it means that you actually have to touch objects, either with your hands or with light or whatever apparatus. And that the touching, the actual physical contact, the interaction with the rest of the world, distorts the other measurement. If you look at this derivation, that's simply not true. I haven't said anything about how I've measured things. The only thing I've said is, well, any information state, cat, can be written as a linear combination of eigenstates. That's where it came from. And the fact that that is true is completely irrespective of whether you touch things or not. So, again, in some books, especially the older books or the more popular books on quantum mechanics, you will find, well, you cannot measure two things at the same time because one measurement, just by touching the stuff, will distort the other one. No, it's much more fundamental. It's already built in there in the axioms. And it's important, that's important to note. Now, let's do a couple of examples. Erase all of this. Everybody okay? So we're going to take our beautiful, beautiful, beautiful Heisenberg uncertainty relation. Well, let's calculate a couple of uncertainties. Here's one. In exercise 2, there were a number of commutator relations to derive. And the most famous one, the one that you will use the most, is the one that we proved last time. The commutator of x and p in separate directions is given by a times h bar delta ij. We proved that one last time. Okay, we also proved this. So we have two true statements. We're going to plug it into each other, see what happens. The uncertainty of x in I direction times the uncertainty of j should be equal or greater than, this is up to you, this part.
How are you doing it?
Sorry?
How are you doing the proof?
No,
Or are you just getting
just ask you to plug this into that and see what comes out. Well, there should be at least an I there. And then the average, oh, and h bar. And then the average of delta. Okay, what's the average of delta?
Half.
1/2? Oh, because one sometimes it's 0, sometimes it's 1, so the average is half.
Oh, I think I saw what I was confused with, because there is the inequality is bigger or equal to I times, if there is that's going to be equal to half, and the I is only in the commutator.
Yeah.
Shouldn't
Oh, you're right. Oh, excuse me. No. Oh, no, thank you. Look at me making a mistake. Let's see. I times C, yes? Because that was our premise. That should be written as this. So C is this part. This is C. And it should be I times the average of H bar of this. So I think this is correct. I think this is...
No, I was looking all the way to top.
Yes. Oh, yeah.
But shouldn't that I be a half?
You're right. And that was wrong all this time on the board. So feel free to go through your notes and replace that I by 1/2. Yeah.
Also, I think that I don't think it's half. Yeah, we're trying to count that, but it's only 1 at one point and then 0.
Exactly. So it's more like a Dirac delta function than something else. And what's the average of a Dirac delta function? That's difficult.
Yeah, it's yes.
Yeah. You're right. Ryan. Yes? No, I'm just teaching myself what the names are. Okay. Yeah, they should have been on 1/2 all this time. It's me, it's a typo. mean, there's no mathematics. There's no mathematics wrong. It's me having made a typo. Sorry about that. This I is there. I mean, this is the correct one. This was just a typo of mine. Anyway, so 1/2. So that means it should be no I there. It should be 1/2. Let's see if there's no more typos now. I times C should be 1/2, and then the C, so the I is dropped. Is that correct? I think that's correct. Okay, so there's 1/2 H bar, and then the average of this one. Well, in order to find out what the average of that one is, just write it out. Because we know that the average of any operator is just squeezing the thing between two brackets. Like this, yes? Now, one thing I know about the Kronecker delta, it's either 1 or it is unity. It's either 0 or unity, but in both cases it's going to be a number. So whatever the number is that comes out, you can put it in front of the bracket. So you gives you a bracket, psi, and here's postulate number 4, 3 days ago. You can normalize these things. So this, because it's the same, it's a bracket of the thing with itself, it's just unity, it's ij. And that gives us the famous Heisenberg uncertainty relation. Here's the general case, but the way that you mostly encounter it in physical practice is for momenta and position. And there you go, there it is.
Wait, so the I is cancelled out because of...
There's no cancelling out, it's just a matter of definition. In my original premise, in the big derivation, we had this.
Yeah.
That one. And if you compare it to our Heisenberg one that we proved a couple of days ago, you can see that this part, everything except for the I, is what we call C. And then it says you plug in the C, forget about I.
Why forget about that?
Because what we have to plug in here is the thing that we call C. And if you compare that to that, then you see that C is this part. There's no I.
Yeah.
Okay, can somebody give me a physical interpretation of this thing? So I have this coffee cup flying around here. This is X. This is Y. Say it's flying, happily flying along. I measure its position. What does it tell me about the momentum if I have the position measured with some certainty?
You cannot measure a certain momentum in the same direction.
Exactly, I was looking for that last word.
But you can do it in a different direction.
Exactly.
Because then the delta is going to be 0.
Exactly. I built up this question with the idea that someone would say you cannot measure momentum. I would say, aha, in all directions. And then the answer would of course be, well, if it's in different direction, then there's no problem whatsoever. Because at the moment that the coffee cup is flying in that direction and you measure its X position with a certain degree of certainty, and you want to measure its momentum in Y direction, then the Kronecker becomes 0. And that allows you to calculate to know either, well, individually, but either both of them with 100% certainty. Yes.
And the I and J subscripts, and they're representative of direction, right?
Yes.
Shouldn't they both be I's if you're saying only in the same direction that it follows the uncertainty principle?
Well, actually, this is a brief statement of both two statements at the same time. If they are in the same direction, so you can split up this into different expressions. If they are in the same direction, so they're both I's, which is your case. In that case, Kronecker delta becomes unity.
Yeah.
Yes. If they're not in the same direction, so it's a J and J is not equal to I. So if you get delta xi and delta pj, which is not I, then it should be that one. So it's really just two statements at once.
Yeah, okay.
Now, if you go back to this hand-waving way of looking at the Heisenberg uncertainty relation, namely that you distort the experiment by touching it. Again, it's not true. The uncertainty already follows from postulates. No measurement involved. But suppose that we do follow that way of hand-waving way of thinking. It sort of makes sense, yes? If the coffee cup is flying in this direction, like this, and I measure where its X position is, which means I have to push it against something like that. Has it changed its velocity in y direction, its momentum in y direction? The answer is no. You can very easily measure its x position, put a screen somewhere and see where it bounces. It hasn't changed its y momentum. On the other hand, if it's flying in this direction and you want to know where it is, so you shoot a photon against it or something like that, then you sort of distort it just by conservation of momentum, right? You give it a little push. At that moment, the measurement in x direction has changed its momentum in x direction. Not in y direction. Shooting a photon in this direction doesn't change its momentum in that direction. So, even from a hand wave point of view, this sort of makes sense. But I hope that you see now that it comes out of much deeper principles. So there we go.